Okay, great. Yes, today I'll be talking about how the difference in the experimental protocol for the standard CMIP simulations and the HighResMIP simulations affects the historical simulations. And this work is partly funded by the ERIE project as well. Yeah, with a lot of help from Malcolm Roberts. So, as an introduction, then. This schematic shows the difference in the experimental design for HighResMIP simulations versus the standard CMIP DEC simulations. So the bottom section, shows the sort of protocol for the CMIP simulations, which starts in 1850 with a very long spin-up, multiple hundreds of years and a 500 plus year of control before starting the historical simulations, which goes up to 2014. However, for high resolution models, this is often prohibitively expensive. Simply can't run that many years. So HighResMIP, to get around this problem, used a slightly different experimental protocol, where they start from 1950. That's where the control, that's the baseline for the controls, and with a shorter spin-up period of 50 years and a shorter control of 100 years. So then the historical simulation is only from 1950 to 2014. The other simplification that HighResMIP made was for the aerosol scheme. All models that participate in HighResMIP use the prescribed easy aerosols, whereas for CMIP, there was no such requirement. So modeling center could use whatever aerosol schemes they want. So for example, at the Met Office, the GLOMAP mode scheme was used, which is quite a complicated one with both direct and indirect aerosol effects. Another thing to point out is that more and more high-resolution models are adopting a HighResMIP-like protocol. So, for example, Destination Earth, which are running sort of tending to kilometer scale models, are using a 1990 control simulation. So I think it's interesting and also probably important to link these new generations of higher resolution model to the more traditional CMIP class models to really understand how they relate. Okay, so the first result I want to show is the ensemble mean of the CMIP6 models versus the HighResMIP models with their respective historical simulations. And ERA 5 is shown in red, and the CMIP6 models are shown in black, and the HighResMIP ones are in blue. So perhaps a bit surprisingly, the ensemble mean of the HighResMIP models are slightly cooler than the CMIP6 models. And I guess it's surprising because starting from a 1950 baseline, you might expect them to be slightly warmer. However, the caveat here is that, of course, there are many more. There are like 50 odd models for the CMIP6 ensemble and only 15 for the HighResMIP ones. So to get a better look at things, I have selected the sort of modeling centers which ran both the HighResMIP and the standard CMIP DEC simulations. There are only 5 of them that have done this. And we see that, okay, so the pale lines are the DEC simulations with the different models used by, say, CMCC at the top left. And the darker lines are the HighResMIP simulations. So the dashed line is the high resolution version, and the solid line is the low resolution counterpart running the HighResMIP experimental design. So we can see that, especially for the Met Office model and the CNRM model, the HighResMIP runs are indeed cooler than the CMIP runs, and it's not just because of the resolution difference. Both the dash and non-dash lines for these two modeling centers are really below any of the other CMIP6 runs. It's not so clear for the other modeling centers. Maybe CMCC shows a cooler, high resolution version, and ECS kind of sits within the ensemble, but maybe tending towards the cooler end. But none of the HighResMIP ones are warmer than the CMIP counterparts, actually. So there does indeed seems to be a slightly cooler bias in the HighResMIP ensemble. So to understand this a bit further, we've looked at the Met Office model a little bit deeper. And the reason for this is that the HiGEM3 model run by the UK Met Office is the only one that has run both the HighResMIP and CMIP experiments using the same configuration. The other modeling centers have slightly different models that are used. So yeah, the following analysis tries to understand this difference. So again, this is on the left panel is a similar figure shown before, where the black line shows the sort of 1850 historical simulation that's used in CMIP, and the blue line is shown for the HighResMIP historical run. And just another thing to point out, these results are all shown for the low resolution version of the HiGEM3 model. So the only difference between the black and blue line here are the experimental protocol. The resolution is the same. So although it's HighResMIP, it's the same resolution. So yeah, so we can see that it's significantly cooler in the HighResMIP run of the HiGEM model. It's about 2 Kelvin cooler, which is quite a lot. However, when you calculate the anomalies with respect to the control, the two lines are much more comparable. The HighResMIP runs are only about 0.2 Kelvin warmer in terms of anomalies, but the rate of warming seems to match much better. So 2 questions stem from this. What is the reason why there's such a big difference in the sort of absolute value of the historical run? And are the anomalies really that comparable between the 2 set of runs? So I'll look at the anomalies first. So a further look at the anomalies, we look at the spatial pattern of the surface air temperature. So that was the global mean before. Now we look at the pattern of what it looks like. So ERA 5 is shown at the top left, showing the difference in the first 3 decades of the simulation compared to the final 3 decades of the simulation. So the 1984 to 2014 minus 1950 to 1880. So you can see this, warming pattern everywhere across the globe, with the poles warming much quicker than the rest of the world, and this sort of warming hole pattern across the North Atlantic that's probably quite familiar to most of you. And in the middle panel, we showed the difference between the 1850 historical run minus ERA 5 and the 1950 historical run minus ERA 5. Sorry, that label's wrong. At the bottom right here, we showed the difference between the HighResMIP and the CMIP pattern. And I think focusing on this pattern, we see that actually although the time series looks similar, the 1950, so the HighResMIP version of the historical run doesn't really capture this warming hole pattern at all. So which suggests that this sort of variability might not be captured properly in this simulation compared to the CMIP one. So although the time series look quite comparable, actually there are some regions which don't match so well. So just taking the anomalies doesn't solve everything, basically. And so, moving on. The second question we looked at was, why was there such a big difference in the mean in the absolute value here, why is there such a big difference in the two runs when the only thing that's different is the experimental protocol? And this figure shows the TOA shortwave. Spoilers, it's the aerosol difference that caused this big difference in the absolute value. So, so the darker line on the left on the time series are the 1850 controls, and the pale lines are the 1950 controls. And the pair of blue lines are additional experiments with RAN, which controls for the aerosol. So remember, for the red line here, the METOFIS model used the GLOMAP aerosol scheme, and for the pale line, they use easy aerosols. For the blue lines, now we've used GLOMAP for both. And the difference between these two pairs is shown on the right-hand side here. So when we use the same aerosol schemes, the pattern of TOA shortwave is what you would expect the difference between 1850 and 1950 to be, namely this sort of northern hemispheric pattern that's centered on the US and the European continent to do with the industrialization, as opposed to this pattern in the GC3 model where there was a uniform, less outgoing shortwave in the 1850 control. Therefore, it was warmer. It was uniformly warmer by about 2 Kelvin. So there's which explains this big difference in the TOA shortwave and also the temperature. So
5 minutes, Michael.
Okay, thank you. So once the aerosols are accounted for, this is a control with the HatGem model. So the black line is the 1850 control and the blue line is the 1950 control. They are much more similar. It's not that 2 Kelvin offset we saw before. So once you account for the aerosols, the next biggest impact on the difference between the two runs are the spin-up length and the baseline. So the red line shows the version of the control where if the ocean was spun up already, what would the 1950 control look like? And it's as you expect, it's a bit warmer than the 1850 run. And it's a lot more comparable to the PI control than we saw before. So just to conclude, this is still a bit of a work in progress. We've identified that aerosol is a big source of difference between the CMIP runs and the HighResMIP runs in the METOFIS model. Once you account for that, the two controls are much more comparable, and there's ongoing work to quantify the impacts of the shorter spin-up and the 1950 baseline. I guess that's my conclusion at the moment. But I think throughout this analysis, a few interesting discussion points I think came up that would be probably good to have some feedback from the community. Is how one of them is how should we talk about climate change in terms of absolute values or anomalies? So climate change is often expressed as anomaly. So 1.5 degree warming, 2 degree warming, but many impacts are quite sensitive to the absolute values instead, like threshold-based things. Like heat stress and so on, or nonlinear responses to do with sea ice and precip. So, obviously there's a big spread in the absolute values in the CMIP models. What is the best way to think about that? And and the second point is about the controls. It seems to be that as models move towards higher resolution, they're more tending towards the HighResMIP-like control simulations. How should we think about this going forward? How should we better link the standard CMIP models with the newer generations of high-resolution model? And and some variables actually might be more comparable between the two controls. Surface air temperature is probably the most sensitive to the experimental design differences. So there are still a lot of sort of outstanding questions, but would be good to get people's opinion on it. That's me. Thank you.
Thank you, Michael. Do we have any questions? Anybody put your hand up if you've got any questions? I don't see anything in the chat, but if you've got any questions, feel free to ask. Helene's got a question.
Hi, Michael. So do you think that, I mean, that's really interesting. Do you think it kind of puts the emphasis back on trying to get fast spin-ups of the ocean?
So, yes, I think so. I think one of the disadvantage of the shorter spin-up is obviously there's going to be more drift. So having as fast a spin-up of the ocean would definitely be ideal, especially if it spins up to something where we have better observations, so the 1950 conditions. There's also some evidence that higher resolution models do spin up faster, so the GFDL preprint showed this, and some of Malcolm's runs also showed this. So, you know, the results I showed were only for low resolution models, so maybe the spin-up issue is less important as you go to higher resolution models. Yeah.
Okay, thanks.
Thank you.